All right, welcome to the Kitchen Research Group. I'm happy to tell you today about a paper we had recently published on the high-throughput discovery of ternary copper-iron ruthenium alloy catalysts for photo-driven hydrogen production. So the idea is down here we have a high-throughput system where we can test lots of different compositions of copper, iron, and ruthenium and map this onto an activity map where we have ternary catalysts that are better than any of the pure metals or the bimetallics. Now, in a nutshell, we have a need for hydrogen production with renewable energy. We're going to use light in this work, and renewable feedstocks that include oxygenates, things that are bio-derived, and eventually maybe even water. So the idea we have here is that iron is earth abundant and copper is pretty abundant, and iron on its own is pretty good, but the combination of these you'll see is even better than that. So we have a high throughput reactor system that we can put different experiments in down here, shine light on them. The light works with a photosensitizer to create an excited state that can reduce metal ions to catalysts or oxidize something like TEOA or some other hydrogen producer. So we use this to find a unique set of compositions in copper, ruthenium, and iron that normally are immiscible, but together they form a very active material. All right, so I'll go through the main features of the paper. We looked first at the individual metals. So on the right here, we have copper, ruthenium, and iron. This is the amount of hydrogen that's been produced with those. You can see that copper's not very good. It doesn't make very much hydrogen. It makes a little bit. It does make particles. They're just not very active for making hydrogen. Ruthenium is basically dead. We hardly find particles anywhere, and we don't see any hydrogen production. And as we go through, starting at low iron to high iron, all of these are sequences in concentration. You see iron is actually quite good at making hydrogen. It also makes good particles. Now, our previous work suggested these are not metallic iron, but maybe iron sulfide particles. But it doesn't actually matter. What we know is that it makes a lot of hydrogen in this case, and iron is earth abundant. All right, when we go to bimetallics, each one of these points is an experiment in that well. So there are probably about 100 experiments in here spanning different concentrations of copper and ruthenium. And even though we know copper and ruthenium are not that good, you can see when we combine them, we get pretty interesting activity and good activity. So copper and ruthenium somehow individually are not good, but together are pretty good. If we look at copper and iron, you can see over here that at the highest concentrations, the largest circles of iron, we get pretty good activity. But with some combinations of copper and iron, we get even better activity that's higher than either one of those. And again, we see the same thing over here with ruthenium. This is the iron and ruthenium. Ruthenium is dead, but the combination of ruthenium and iron is better than either one of those. All right, so by using two metals that are not necessarily miscible, we get improvements in activity. Now, looking at these, we can see that copper-iron, we see nice particles that form, and you see co-location and concentration of particles. With copper-ruthenium, we also see particles. That's not a surprise because copper makes particles, and you see some kind of co-location here. But with iron and ruthenium, it's a little less clear. We see well-defined particles. Iron makes good particles, but you see lots of kind of a mix of where ruthenium is and where iron is, not always co-located in the images. So some of this is not super surprising. These metals are not all miscible. They don't all form alloys. Okay, we can go to the ternary mixtures. So there we take in our 100 well plates, 96 or 108 depending on the well, our plate, we can have different combinations of iron, copper, and ruthenium. And here the color is an indication of the hydrogen production. So red is the most active. And you see a few regions where the ternary is much more active than anything on an edge, which would have been the binary or bimetallic, and certainly better than the corners, which is the pure metals. Similar to what we saw before, we have a distribution of particles in composition, a distribution of particles in size. We see good particles forming in regions where things are active, and a distribution of co-located elements down here in the elemental analysis spectrum. So we get a kind of distribution of mixed composition particles and sizes, but it is unambiguously better, and a lot better than anything we see on the edges for that. All right, so that's the summary of our paper. The discovery of this was somewhat serendipitous. Sometimes in catalysis, a common way of discovering catalysts is to make a material, characterize it, make sure it's well characterized, and then test it. That would not have found this discovery here because it's not a well characterized or well behaved material in the sense that it's a distribution of things. So in that sense, it was serendipitous that we put the things in. We were able to do hundreds of experiments in the high throughput reactor and find that there was something interesting, and then find out why was it interesting or what was happening in there. So that high throughput approach was essential to be able to do all of the mapping and experiments. If we did this one at a time, it would have taken forever, and probably we would have given up earlier. This ternary doesn't form a single material. It has a distribution of particles. We don't know which ones are responsible for the activity. That's a whole focused effort that needs to happen in the future. But the ternary is better than either the single or bimetallic, and we think this is an exciting approach to find new materials that are improved over existing ones. So that's it for the paper. Thanks for listening, and I hope you enjoy it.